Come on in, everyone. Anybody have any questions before we get started? I look forward to yawning with you for the next hour and 20 minutes. All right,
Hey, Professor, I got a question about the practice test.
good for it.
Does that does that lock at midnight tonight?
I think I just changed it. Let me double check. I want to say I just changed it, but I might be misremembering and doing something that I did for another class. You're talking about the online test that I called Practice Test 3. And
Practice test F2 FT01, chapter
oh,
17 and 18.
yes, that's right. I opened that back up for people that just didn't take it. I give them another chance. Uh, so yeah, it's tonight or nothing. But it's not like there's a test tomorrow. It's just for the test.
So that's only for those that have missed it.
No, if you didn't get 100, you can use it to make sure you get 100 because it takes the highest score from each practice test you had. It takes the highest score. So if you scored nothing as high as 100, then by all means take it again so you can get 100. But other than that, you don't need. I mean, if you already have 100, you don't need to take it again.
Okay, awesome,
Okay,
perfect. Thank you.
you're welcome. Anybody else have any questions? All right, so we're starting into the difficulties of electricity and magnetism. Specifically, we're starting off with Coulomb's law in integral form for the electric field. So there was Coulomb's law that was just a statement of the actual magnitude of the force, which was given, if you want to use the crappy constant, it was given by K, Q1, Q2 over R squared, where Q1 and Q2 are the two charges. That shows you the force is directly proportional to the product of the charges. So if you increase one charge by a factor of 2, you're going to increase the force by 2. If you increase the other charge, say, by a factor of 3, then you're going to increase the force by a factor of 3. If you increase the first charge by a factor of 3 and the second charge by a factor of 4, then you're going to increase the force by a factor of 12. And also it's 1 over r squared because it goes like 1 over r squared, where r is the distance between the center of mass of Q1 and, or excuse me, the center of charge of Q1 and the center of charge of Q2. Uh, in that case, if you double the distance between the two charges, then you cut the force by a factor of 4. If you triple it, you cut it by 9. If you cut the distance between them by a factor of 4, then you increase the force by a factor of 16. If you cut the distance between them by a factor of 5, then you increase the strength by a factor of 5 squared, which is 25. And it said also in Coulomb's law that the force acted along a line connecting the center of charge of Q1 and Q2. That was basically Coulomb's law, which looked exactly like and was even explained like Newton's law of gravity. The difference being that like charges repel, and there's no such thing as a repulsive gravitational force, and unlike charges attract. So positive and a negative are always going to be attracted to one another. That's acting like gravity. Whereas a positive and a positive or a negative and a negative is always going to act repulsive, which gravity doesn't do. Okay. Then we said, well, let's think instead of dealing with a force due to charge 1 and charge 2, let's imagine that the space around a given charge, say capital Q, has been distorted in some way. And that distortion is basically the Coulomb force divided by the other charge. So if Q1 was made into big Q, then the electric field would be K big Q over squared, or the way I prefer to do it, which is big Q over 4 pi epsilon naught R squared. That's the electric field, and specifically that's the electric field strength at a distance r away from the center of charge of big Q out to some distant point P. Uh, like I said, that's a distance r away from the center of charge Q. Okay, that that electric field acts in such a way that it tends to move a positive charge in the direction that a positive charge would go as a result of the electric field. So if the charge big Q, for instance, were positive, and let's say it's right here, then if you put a test charge over here positive, then that charge is going to want to run away from it and go along the line connecting the two. Okay. So from that, I was able to get you guys to this particular equation, and that is the differential portion. And I'm going to go ahead and share my iPad with you guys now. But the differential of an electric field, dE, is equal to, and like I said, I'm in the process of trying to share this with you. The differential electric field is equal to the differential charge dq divided by 4 pi epsilon naught. And then what I did was I invented a vector that points from the origin to the point P at which we wish to know the electric field. And I invented another vector. In this case, it'd be R sub dq, which points from the origin to the center of charge dq. And then I subtracted those two, Rp minus R dq, and took their magnitude so that that would actually be the distance between the point P and the source of the charge dq. And I wanted to make it into a vector equation. Now, in general, this magnitude should be squared, but I really would like to multiply by a unit vector, which I don't have. I have a vector pointing the right direction. That vector is R minus R dq, and that's, of course, RP minus R dq. Let me make sure you all are following that. So RP minus R dq is the vector that points in the right way. But when I multiply that by that, I basically increase the electric field strength by a factor of what we had been calling R. So what I need to do to account for that is I need the R to be R squared in the bottom and to account for the extra R I need. So I put the R minus RP minus R dq absolute value, I put in, well, absolute value, which means magnitude, I put to the third power. Okay. So just as a quick reminder, what we're suggesting here is you have a space this might be, for instance, X, this might be Y, and this might be Z. And now we have a little bit of charge dq. And what I'm saying is this vector is R dq. And then I have a point in space, which I'm going to call point P. And that vector from the origin to it is called R sub P. And then, of course, we can create another vector by, by subtracting RP minus R dq. Okay. Notice that is exactly the vector that points from the center of charge dq to the point P in question. So it definitely points in the right way. Notice also that its length is the distance between the center of charge of dq and the point P. So its magnitude is actually the R we're looking for. So that's the formula we're going to use. So first I'd like to consider an infinitely infinitely long, let's start with that, long charged straight insulator of uniform linear charge density lambda and compute the electric field a distance r from the long insulator. And I'm saying it's an insulator just because insulators have this property where basically the charges aren't free to move around. So if I put it in an insulator, you can go on the assumption that not only is the charge uniform like it says, but it's going to continue to be uniform. So what I'm going to do is draw this in a coordinate system as I wish to do. Okay. In other words, the problem didn't give me specifically a way to solve it. It didn't give me specifically a coordinate system I'm supposed to use. So I'm making up my own coordinate system. My coordinate system is basically going to be this vertical y-axis. And it's technically a three-dimensional problem, but the symmetry of it allows us to pretend like it's a two-dimensional problem. So what I'm going to do is I am going to draw the wire like so. Okay. And I'm going to point out that it goes to infinity that way and goes to infinity that way. And now I'm going to go over here a distance r away is going to be the point P at which we wish to know the electric field. Now, in principle, we could rotate this whole picture about the y-axis, maybe like 5 degrees. Then the x-axis might be sticking out of the page by about 5 degrees. And we would still have the R being right there and still be a distance R away from the center of the wire. But we could also put the x-axis back on the page and it'd still do the same thing. And I could keep doing that over and over. And you'd see that every time, basically, the electric field is going to point radially outward from the y-axis. So we're going to get an answer in terms of I hat. The j hat term is going to cancel out, but we're going to get a electric field vector in terms of I hat, so it only points in the positive x direction. But in reality, because of the symmetry, we could rotate this by any number of degrees and still get the same answer. So basically, that I hat is really what we would call the r hat vector, or the vector that only has x and y components that point radially outward in, say, a cylindrical coordinate system. Okay. So how are we going to do this? Well, I first need to point out all the little vectors. So we need a vector that points from the origin to the point at which we wish to know the electric field. I'm going to choose, let's choose the purple vectors for this. So from the origin to the point P would be this vector right here. So that's going to be called R. Oops, almost read it as RDQ. That's supposed to be RP. Okay. Now I'm also going to imagine a little bit of charge on the actual insulator. This bit is what we're going to call DQ. And what I will say is that thickness right there is dy, and this distance from here to here is y as well. So that will help me not only identify what dq is going to be in terms of the lambda dl, sigma d rho, or rho dv, excuse me, sigma dA or rho dv, it'll also help me figure out what r dq is. So if I draw a vector from the origin to the little bit of charge dq, that would be this vector right here, which is r dq. Okay, and this dq, we talked about it being a linear charge density, and remember that the choices are dq is equal to lambda dl, or it's equal to sigma dA, or it's equal to rho dv. I'm using this one, and that means it's lambda times the thickness, which in this case is dy. Okay. So all I really have to do is compute what is RP, what is RDQ, and so on and so forth. So RP, you guys should be trying to guess what this vector is already. Hopefully you already did, and be doing the same thing with DQ. I'm getting ready to write down the answers, but I really think you guys are supposed to be skilled enough to look at that vector and know exactly its magnitude and direction. And then maybe you might not have all the details on how you're supposed to write it, but if you can at least tell me the magnitude and direction of RP, then I would say you're doing it right. Do the same thing with DQ, RDQ as well. I'm going to go ahead and write the answer for RP now. Now the answer to RP is its magnitude times a vector that points in the positive x-axis, the positive x direction, because RP points to the right, which is the positive x-axis. So I'm just going to say R times I hat, and that's exactly the right answer. Hopefully y'all all got that. Now that you know that, try again with RDQ. So notice RDQ also has a magnitude. Hopefully I've already figured out what that magnitude is. I took the time to explain things in the diagram enough where you can see it. And I think you can also tell which direction it points. It points vertically upward, which is the positive y direction. So hopefully you all have already reached a conclusion that it is y times j hat. Okay. And then that means, of course, RP minus RDQ, which is also in the formula above up there. Notice that is just going to be the subtraction of the vectors. So that's going to be RI hat minus YJ hat. And in fact, that vector points from here to here. So this is literally RP minus RDQ. And that alone should be able to tell you what the magnitude of it is. But if not, then you can, of course, use the Pythagorean theorem and use RP minus RDQ. I'm going to go ahead and write it down. Hopefully, you've already figured out what the magnitude of RP minus RDQ is. I'm going to write it down now. So the magnitude of RP minus RDQ is actually equal to, notice it's a right triangle. The horizontal leg has a length r and the vertical leg has a length y. So it should be the square root of r squared plus y squared is the magnitude. We've also gotten dq figured out to be lambda dy. And we were given lambda, so that's a quantity we know. So we can now proceed to work out what exactly is E. So the electric field E is equal to the integral of dE, which equals, I'm going to go ahead and pull out the lambda and the 4 pi epsilon naught. So lambda over 4 pi epsilon naught. Notice that is just part of the dq and then the 4 pi epsilon naught from the formula above. Now the rest is going to be the integral of, now I've already pulled out the lambda, so all I have left of the dq is dy. And then I've already got the 4 pi epsilon naught down in the bottom, but I need the actual distance cubed here according to the formula. So that's going to be r squared plus y squared to the 3/2. Remember, the 1/2 gives you the r value or the distance, and then you got to cube it, so that makes it 3/2. And then I also got to multiply by rp minus rdq, and of course that's r I hat minus y j hat. So that's the integral. And if you were able to write that, and I was doing a typical test where it was just a handwritten test you turn into me, if I saw you got that much, I would basically give you probably 95 to 98% of the points on that particular problem. So that's the most important part, is can you get that? Okay. Now this does break up into a couple vectors or a couple integrals. So I'm going to do that part so we can make some sense out of it. This is going to be 4 pi epsilon naught down here in the bottom. I'm going to put curly brackets here, and I am going to say r times the integral of dy I hat over r squared plus y squared to the 3/2. That's my x component. Minus, I'm going to put the y out front as well. Oh, I can't put the y out front because that one's actually an integrand. So I'm going to leave that. I'm going to say the integral of y dy j hat, all that over r squared plus y squared to the 3/2. Okay. Now, this is, you'll notice if you've read the book, your author's doing something that I would call mathematically ingenious. There's a nice mathematical way where you can simplify this to make it, or actually, I would say maybe it's not mathematically ingenious, maybe it's physically ingenious. And I go on the impression that pretty much when you are taking your physics, calculus-based physics, you have very little, if any, experience with physics. So I would say you might be a little bit more savvy at being mathematically ingenious than being physically ingenious. So that's why I'm giving you the nuts and bolts of the mathematical calculation rather than making a physically cute approximation. But to explain what he did is basically you can imagine him creating a dE vector right here. That's the dE vector he's talking about. And you would maybe call this angle right here theta, which by the way is the same thing as this angle theta. So that's going to come in handy. But what you might notice is right now that vector dE has an x component that points to the right, and every other dq that we put will always have an x component pointing to the right. Do y'all see that? Do you see if I go further up to higher and higher values of y, I still get a y component, or excuse me, I still get an x component that points to the right. And if I even go below the origin with y pointing downward, I still get a x component of dE pointing to the right. Now, what you also might see is there's a y component to this dE, which let me draw it right here in yellow is probably not going to show up too good there. I'll draw it in this gray color. So this right here is dE sub y. Now, if you consider going the same distance away, let's say right about here, and then this quantity, of course, from here to here is y, you'd see that this vector is going to have exactly the opposite y component as the other one did. And for every dq you can find on the positive axis like that, you're going to find a dq on the negative axis that's symmetrically placed, and therefore the y components are always going to cancel out. So you see that ultimately this integral right here should go to 0 just from the symmetry. So just from symmetry, it should go that way. I'm going to actually take the time to show you it doing that as well. So I'll show you mathematically how it works out as well. But the main thing is I wanted you to know physically that's what we're doing. And physically what he did was at this point, instead of using a complicated formula, he basically just used the typical formula for the magnitude of the electric field, which would be dq over 4 pi epsilon naught r squared, and then multiplied it by cosine of theta to get the x component. And then he just integrated that from, theta equals 0 to infinity, and then doubled it because of symmetry. You expect you're going to get twice as much from the total as you get from the positive x-axis. Okay, so that's really what he did. What I'm going to do right here for this portion is I'm going to say let y equal r tangent theta, and then dy will become r secant squared theta d theta. On this part right here, because I told you I'm going to show you at 0, I'm going to say let u equal r squared plus y squared implies du is equal to 2y dy. Oh, I'll write that on another page so it won't be so hard to follow. So what I'm going to say is this, whoa, Nelly. What I'm going to say is this implies du is equal to 2y dy, which we already have a y up top, so I just need a 2 there. And then if I multiply by 2, I need to multiply by 1/2 as well. So this part right here is just going to be du. And this part down here is just going to become u. Okay, so that's what I'm going to do as far as computing these integrals. I will continue from right here. I'll say lambda over 4 pi epsilon naught, curly bracket, r is going to be right here. Now, notice I have dy is going to be r secant squared theta. So now I got a r squared there instead of an r. So then I'm going to get the integral of secant squared theta d theta. And not only that, I'm going to get a common factor of r squared, so I can pull that out in front from both of the terms in there. And then this is going to be 1 plus tangent squared theta. And all that's going to be to the 3/2 power. And all that's going to be times the I hat. Okay. Now, hopefully what you'll see is the r squared in the bottom will be acted on by the power of 3/2. So the 3/2 is going to cancel the 2 with the 2 in its denominator. And I'll end up getting r cubed on the bottom, and r squared is already on the top. So in fact, I just get 1 over r for the r's. 1 plus tangent squared, of course, is secant squared theta. Of course, it's raised to the 3/2 power, so that's going to be secant cubed theta in the bottom with secant squared theta on the top. So that's just going to be 1 over secant theta. And of course, 1 over secant theta means cosine theta. Okay. Now the other one's going to be a little easier. I'm going to write -1/2. Now I'm going to say the integral of u to the -3/2 du. And that's the integral in its entirety for that second part. Notice I did carry the negative, and I also got to put the j hat here. But now I can close my curly brackets. So now what I'm going to do is say I'm going to use up a little bit more space by coming over here to the left. I'm going to keep my lambda over 4 pi epsilon naught out in front. Now my curly bracket, we already worked out that the r squared in the bottom is going to become r cubed, and that it's going to cancel out with the r squared on top. So I'm just going to get 1 over r here. I also am going to get the integral of cosine theta d theta, which you can now see, oh, yeah, when Giancoli multiplied by cosine theta to get the component in the x direction, he basically did the same thing that I just did, which is, put the cosine in. All right. So we've got that. Now I want to point out something neat. When I did y equals r tangent theta, that trig substitution basically made this angle theta such that r would be the horizontal leg and y would be the vertical leg. And in fact, this part right here would be r squared plus y squared square root. But the main thing is when we see that, we can say, oh, well, that's easy enough. We're going to integrate from theta equals, well, actually, what we'd end up integrating for in this case was theta approaching negative pi over 2 to theta approaching pi over 2. Because notice as theta goes to 90 degrees, y goes to infinity, which is really what we were initially integrating from. So I'd say from negative infinity here, for instance, to positive infinity, that would have been our range of integration to begin with. Okay. But sine, the derivative of sine is cosine theta. So the integral of cosine is sine. So we're just going to get the sine of theta. But what I can do is you'll notice cosine theta is what we call an even function. And even functions, when you integrate them over a symmetric range, like negative pi over 2 to positive pi over 2, that's symmetric. It goes from the same value on the left as it goes to the right. Because of that symmetry, I can just multiply this by 2 and then go from 0 to pi over 2. That works as well. So that's another option we have. In the case of the other integral, we're going to have negative 1/2. And then when I integrate u to the negative 3/2, I'm going to raise u to the negative 3/2 plus 1 power, which would be negative 3/2 plus 2/2, which would be negative 1/2. And then I got to divide it, of course, by negative 1/2 because that's what happens when you integrate. Okay. So that negative 1/2 out in front is going to cancel out with the negative 1/2 that we just got from the integration, and it's going to make that positive. And what we're ultimately going to get is basically just u to the negative 1/2 power. So this would be 1 over uh, r squared plus y squared to the 1/2 power. And this one I'm going to evaluate from y approaching negative infinity to infinity. And that's my curly brackets. Okay. I think you can see that because this is the integral that we got, notice that's 1 over the square root of r squared plus y squared. If I replaced y with negative y, it wouldn't make a change whatsoever. So basically, when you integrate out to infinity, you're going to get basically 1 over y because y is so much bigger than r. And then when you integrate to negative infinity, you're also going to get 1 over y. And 1 over y minus 1 over y is going to give you 0. So this whole thing is just 0. Now back to the other one. I'm going to now say, since I've gotten rid of that other guy, I'm going to say 1 over lambda over 4 pi epsilon naught r. And now, like I said, the integral of cosine was sine. So I'm just going to put the sine of pi over 2 minus the sine of negative pi over 2, which again, I could have just replaced this and put a 2 up on top, and then integrated and made it sine of pi over 2 minus sine of 0. That would have been fine. But you see what's going to happen is obviously the negative sine, the sine of negative pi over 2, of course, is -1, and negative of -1 is +1, and the sine of pi over 2 is 1. So I get 1 plus 1 is 2. And of course, I still have the I hat there. So now I'm finally going to get that E is equal to, notice that 2 is going to cancel out with a 4 down here. So I'm going to get lambda over 2 pi epsilon naught r I hat. And that's the actual answer. As I said, those symmetry arguments would allow us to rotate this by any finite angle about the y-axis. And then you'd also could make the argument that E is in fact equal to lambda over 4 pi, or excuse me, over 2 pi r in the r hat direction. Okay. And r hat, like I said, is just a unit vector that stays, in some sense, stays in the xy plane. It can actually be up above the xy plane, but it's never going to have a k component. It's never going to have a z component. Okay. And it always points radially away from the y-axis. And with that description, I think you can tell that it is, in fact, the same thing that we just computed. Anybody have any questions on that? All right, so this is a type of problem that you should be able to do between the Giancoli's version, which you should be able to make some sense of, and my version, which you should be able to make some sense of. You should be able to figure out what's going on and decide a way that works for you. If I had my ruthers, I would want you to be able to do them both ways. But I would be honest, to be honest with you, I would prefer you to be able to do it this way, because if you can do it this way, then you can solve any problems. Uh, what's going on, right, like the way Giancoli does, is you're looking for certain symmetries to exist so that you can do certain things. This allows you brute force to set up the integral for anything. And to be honest with you, in physics, it's very rare that we actually get to uh, compute actual integrals in a form that comes out as a nice formula. We normally have to do that by calculus. So you'd have to, write computer code to compute the actual integral. And you being able to do it this way allows you to immediately do that. So does anybody have any questions for this? Notice it's an infinitely long line of positive charges, say. And because of that, the electric field strength only falls off as 1 over r instead of 1 over r squared, which is what it did when we had a point charge. This is also part of the reason why we have fluorescent tube lights. Regular light bulb has the brightness of its radiation falling off like 1 over r squared because it's a point object. But if you stretch that out and make it infinitely long and thin, then you get basically like a long line of fluorescent lights. And because they're basically infinitely long in one dimension, you only have to have the electricity or the light's radiation decrease by a factor of 1 over r as you increase the distance. So that's why the room will feel a little bit more bright and less, shady with long fluorescent lights as opposed to a single light bulb. Now, if you went further and did an infinite plane, you'd actually find that it had zero dependence, and that's why they often put dispersion panels over top of the fluorescent tubes. Anybody have any questions on any part of this that threw you? Hopefully you should notice this is all pretty much bread and butter calculus you're supposed to do in the second semester. Trig substitution, stuff of that sort. It is a bit more. We're actually using calculus, vector calculus specifically, but you can see the way we do vector calculus is if we're using I, J, and K, in other words, X, Y, Z axes, there's no difference. The I hats and the J hats and the K hat can go through integrals and derivatives with no change whatsoever. So no questions on that? Let me put up my chat. It seems my chat's not showing, so least I can do is do that. In case somebody's asking questions there. It looks like no one is. Okay. All right, so we got that one. Now let's use the same sort of formula and see if we can figure out another one. In this case, I'm going to take a coordinate system. I'm going to draw the coordinate system first because I'm choosing a very specific coordinate system. Uh, it's really the best one to use for many reasons. So I'm going to draw a vertical z-axis that way. I'm going to draw a horizontal y-axis that way and a horizontal x-axis this way. So there's my x-axis, there's my y-axis, and there's my z-axis. Now, what I would like to do is I would like to have a ring of charge, if you will, something like that. That was not very good. Let's see if I can do it any better. That looks pretty good. I might even be able to move it up and down a little bit to get it centered up like I want to. Yep, that looks pretty good. It's a little tilted, which it shouldn't be, but that's good enough. What I'm going to do is say, show this as a little bit of length, and I'm going to do that by drawing this little bit right here, getting a little wider there, a little narrower there. Oops, screwed that up. Okay, and that is our basic ring of charge. So consider a circular ring of charge of radius big R and total charge Q uniformly distributed along the ring. What is the electric field at a distance z above its center? Okay, so we're saying the net charge of this thing is in fact Q, but we're also saying it's uniformly distributed over the length. So that means we can actually interpret it as a linear charge density lambda. What I'm going to do right here is say the thickness of it really is kind of irrelevant. So I showed thickness just to show you it's the thickness, but the difference between R and the distance to the outside is essentially negligible. So we don't care too much about that. We are going to go on the assumption that this is the point P at which we wish to know the electric field. From that, we need to be able to come up with our actual formulas. So what our formula is of course dE is equal to dQ over 4 pi epsilon naught divided by the magnitude of RP minus RdQ to the third power times the vector RP minus RdQ. So to do that, we have to find RP, we have to find RDQ, then we have to find RP minus RDQ, then we have to find DQ, and we also have to find the magnitude of RP minus DQ. So we're just going to go through that bit by bit. Uh, when I do this, by the way, I usually choose as my particular charge element. I usually choose that either on the x-axis, on the y-axis, or in the first quadrant. Okay, where both x and y are positive. Uh, the main reason is you often get negative sign errors and stuff like that if you don't. So I'm going to do the same thing right now. What I'm going to do is I'm going to go out a distance r and through an angle theta. And I'm basically going to allow that little radial arm to slide over a certain amount. And that little amount right there is going to be d theta. Okay. Now this distance right here is dl, and that's going to be equal to r times d theta, right? From the formula S equals R times theta, that should give you that length. Does that make sense? Now this little bit right here, which I'm going to color red, that's going to be my DQ. I'm going to say DQ is in fact lambda R d theta. Now remember, it's just an infinitesimal amount to go from this edge that's closest to us to the back edge. So you don't have to think too much about whether you're in the DQ or on the left edge of the DQ or on the right edge of the DQ. Don't think about that at all. What I want you to do now is think about the components of the vector that points to DQ, because that vector is RDQ. Okay, so we can say RDQ sub X is this little guy, and RDQ sub Y is this little guy. Okay, so I can now take and say, let's go ahead and write it in green. So RDQ, actually, I don't like that. RDQ is in fact, notice my x component should just be r cosine theta. So I'm going to write r cosine theta I hat. And my y component is just r sine theta. So I'm going to say plus r sine theta j hat. So everybody can agree that that's the RDQ. Anybody have any questions on that? Okay. Now RP has to point from the origin to the point P. So that's this guy right here. And hopefully you all can see that RP is just, anybody have a guess on that one? You can type it in the chat if you want. Okay. Can you at least think about the magnitude and the direction it's pointing? That's the key thing to getting RP. I think by marking on the axis alpha, there you go. Kaylee got it. So yes, it should be, well, not I hat, but yeah, you're right. It should be K hat. That's the only difference. So very good. That's going to be Z K hat, and that's because it's along the Z axis. But good job, Kaylee. All right, now we're going to do RP minus RDQ, because that's another thing that our formula has. And in this case, it's going to be ZK hat minus r, which by the way, I can factor that out since it's common, and that'll actually help us a little bit. I'm going to write cosine theta I hat plus sine theta j hat, like that. Okay. Uh, that's not necessarily the most convenient way, but when you go to start doing the Pythagorean theorem on it to get RP minus the magnitude of RP minus RDQ, that might make it a little easier for you. So RP minus RDQ magnitude is supposed to be, now if you look at it on this actual screen, you can see it goes from this point down here on the actual ring to there. That's my RP minus RDQ. And I think when you look at it that way, it's a little more obvious what the magnitude is. And that magnitude, of course, would be the square root of r squared plus z squared. Now you can get it from this because remember, a three-dimensional vector, the Pythagorean theorem still works. You take the x component and square it, you take the y component and square it, you take the z component and square it, you add those three squares together, and you take the square root. When you go to do this with this vector, though, notice the I component and the j component, or the x component and the y component, are going to be r squared cosine squared theta plus r squared sine squared theta, which means you can factor out the r squared and you'll get sine squared plus cosine squared, which is just 1. And that's how that came to be. All right. Now we are in a position where we can go ahead and compute the electric field. So I'm going to say the electric field, which is the integral of the differential electric field. I'm again going to make use of the fact that the lambda can come out in front, and this time the r as well. So I'm going to say lambda r comes out in front. 4 pi epsilon naught comes out in front as well. Now I'm going to put a curly bracket up there. And of course, all I've got left for the dq part of the formula is basically d theta. So I'm going to put d theta right here. And then what I have is r squared plus z squared. That's all going to be raised to the 3/2 power. And then what I have is rp minus rdq, which will be zk hat minus r cosine theta I hat minus r sine theta j hat. And of course, all of this has the integral taken over it, and I'm going to integrate from theta equals 0 to 2 pi. Now, what I want you to realize is that this vector right here, let me draw it in black like I did before. It actually goes back behind the page and sticks up that way. So it actually has, for instance, an x component and a y component. In fact, I could sort of draw it like this. Here's my x-axis, and then of course here's my y-axis. So really what this vector is showing is, let me use green here. Let me use a slightly different green. What you see is this one has a x component that goes, say, this way, and then it has a y component that goes this way, and then it has, well, actually I should go a little further. Let's get rid of both of those. So it has an x component that goes this way. It has a y component that goes this way. And then it has a z component that goes that way. The reason why I'm pointing out those x, y, and z components is I want you to see that every little dq that I put on this ring is always going to have a positive k hat component. Okay. But if we choose the diametrically opposed dq, for instance, which would be right over here, then that one would have exactly the opposite x component and the opposite y component. Y'all see that? It sounded like somebody was going to ask something, but that might have been talking to someone else. Do y'all see why that X and Y component is going to disappear? It doesn't matter if you miss it when you go to integrate it. The integration is going to come out to be 0 as well, but this, might be able to allow you to skip the integration. That's the main reason I'm saying that. Anybody have any questions on that? So I'll write right here, this is going to integrate to 0 by symmetry. And this one's going to integrate to 0 by symmetry as well. Okay. I'll carry out that and show it to you in a second, but right now what I'm going to do is say this is all equal to lambda r over 4 pi epsilon naught. I can also write down at the bottom that r squared plus z squared is playing no role in this integral, so that 3/2 is going to be right there. And then all I have is the integral of z, which plays no role either, d theta from 0 to 2 pi, and that's all going to be in the k hat direction. Okay. So when I do that, what I end up getting is lambda times 2 pi r. I'll leave the k hat to put next to it. All that divided by 4 pi epsilon naught r squared plus z squared to the 3/2, and all that in the k hat direction. Can anybody tell me what 2 pi r is with regards to this particular ring of charge? Anyone? So the 2 pi r is really the length of the ring, in other words, the circumference. And since the charge was uniformly distributed along the ring, that means we were able to use lambda as a constant charge per unit length. So if you take the charge per unit length lambda and multiply it by the length 2 pi r, then that's just Q total. So that's what I was trying to get you guys to see. So that's just the plain Q that they told us about. So I can now say that the electric field E is equal to Q over 4 pi epsilon naught. Actually, I don't like that pi. Let me see if I can make a better pi. It looks like I can screw up everything really nicely. So 4 pi epsilon naught times r squared plus z squared, all that to the 3/2 and acting in the k hat direction. So that's really what our electric field is. I could go ahead and show you. Notice that when we integrate with respect to theta, the r squared plus z squared comes out in all of those. So if I wanted to attack those other integrals, what I would end up having is something like integral r cosine theta over or times lambda over 4 pi epsilon naught r squared plus z squared. Actually, that's way too much stuff to fit in that space. So let me start over here. So one term. So we had lambda r over 4 pi epsilon naught r squared plus z squared to the 3/2. All that came out in front. And then all we had was the integral of negative r cosine theta d theta I hat. You can see that that's going to be negative lambda r squared over 4 pi epsilon naught r squared plus z squared to the 3/2. But the integral of cosine theta, since the derivative of sine is cosine, the integral of cosine must be sine. So this is just going to be the sine of 2 pi minus the sine of 0. Ooh, of 0, not 2 pi. And of course, the sine of 2 pi is 0, and the sine of 0 is 0. So we just get 0. The other term is going to be more or less the same thing. We're going to have a lambda r over 4 pi epsilon naught r squared plus z squared to the 3/2 power. That one's also going to have a negative, so I'll pull that here. That's also going to have an r out front, so I will say integral r sine theta d theta. In this case, it's j hat, though. So that's going to be negative lambda r squared over 4 pi epsilon naught r squared plus z squared to the 3/2. And then, of course, the integral of, or excuse me, the integral or the derivative of cosine is negative sine. So the integral of sine should be negative cosine. So I can put that in there, and that'll make that plus. So I'll then say cosine 2 pi minus cosine 0. And of course, the cosine of 2 pi is 1, and the cosine of 0 is also 1. So I basically get equals 0 again. So I've now shown you mathematically that this, in fact, has no x and y components as well. We could have also just seen it by the fact that it was a cosine function over the entire range 2 pi, and you know the integral of sine or the integral of cosine over the whole 2 pi is always going to give you 0. Any questions on that? All right, so those are pretty big ones in terms of some of the complexities involved in integrating Coulomb's law for electric fields. Does anybody have any questions about that kind of stuff? Okay, we can now go a little further and calculate, for instance, the electric field directly above a plate or a disk of charge. But I think I want to go ahead and address the dipole moment thing real quick, because I can do the other thing later. And I really want to get this through to you guys as well as my daytime class. So before, I told you that there's something called the electric dipole moment, P, and that's supposed to be Q times D vector, and that's called the electric dipole moment. And what we're talking about here is, imagine a little negative charge right here and a little positive charge right here. This one has a charge of negative Q, and this one has a charge of positive Q, and the distance between them is D. Then we can actually define the vector D vector as that guy. Notice it points from the negative to the positive, that is what the electric dipole is supposed to look like. So you take a vector and you imagine it beginning on the negative charge and ending on the positive charge. And the two charges, of course, are equal in magnitude but opposite in sign. Once you have that, then you can just take and multiply the Q times the D, and that would give you like Coulomb meters. And that's the units of the electric dipole. So what I'd like to do is consider an electric dipole like that one in a immersed in an electric field. So let's take this negative charge here, and let's take this positive charge here, and let's imagine that it's actually submerged in electric fields that go this way. They're all supposed to be horizontal, even though it doesn't look like I'm drawing them very horizontally. Okay, so there's our electric field. And in fact, our dipole moment vector is right here. So there's our P vector. And I think what you see is that this electric field acting on this charge is going to cause a force that I'll call F positive. And it's also going to cause a force this way that I'll call F negative. Everybody follow that? Y'all see that it's going to compel that positive charge to move to the left and compel that negative charge to move to the right. So in principle, you could imagine it rotating, let's say rotating about that point right there, okay? And the torque would be, of course, force times lever arm. And the way we normally do that is you can sort of think of this is our lever arm, this little vector that points from the center of rotation out to the point of application of force. And what we need is the component of force that's perpendicular to this one. So in this case, this electric field is that way. We could take and find this here. Uh, so that's one way we could actually do it. Let's say also that this angle right here is theta. And I think from that, you can see that this angle would be, if I call that angle theta, yeah, that works. Then this angle will also be theta. And this angle over here on the little green vector that I'm drawing up there, that would be 90 minus theta. Which means this guy, if I drew it again this way, this would be theta. Okay. So now that I can do that, I can take D over 2 as my lever arm. And then I can take my force to be basically the electric field strength, E, times the charge, Q, that's for the positive charge. And I need a component of the component of that force perpendicular to that green arrow. So I'm going to do cosine of theta there. I could use the other angle. That probably would be better. And then I'd get automatic sine. But either way, I can take cosine theta. And now I do the same thing on the other side, and I'll see that that's actually compelling the exact. I'm sorry about the dogs barking. I have nothing I can do. Anyways, that's still going to be E times Q, and we'll get another cosine theta there as well. In fact, we could call that theta, and we might even say this angle. Oops. We could say, since we called this angle, dang it, stop that. Since we called this angle theta, we could call this angle right here phi. And what we would get is T is equal to the torque is equal to D times Q times sine of, actually, no, I want to do sine of phi now. So sine of phi. And if you look at it that way, yeah, that angle really is, I wouldn't say it's that. Uh, I'll just leave it at this. Basically, I was forcing it to use the angle phi so that we could use the formula for cross product. Ultimately, it does work out to be that way. I'll give you the answer right here. Torque is equal to P cross E for an electric dipole. And I put a vector symbol over that, but technically cross products are kind of what we call pseudo vectors. So don't stress too much on that. But yeah, I think you can see either way that clearly the D over 2 with the EQ cosine theta in both of them, those are going to add to give you D over 2 times 2, which ultimately is QD. This part right here, the QD, is really the P. And then what's supposed to be happening is that cross product is supposed to be the magnitude of P times the magnitude of E times the cosine of the angle, or excuse me, times the sine of the angle between them when they're tail to tail. Actually, in the case of, oh yeah, so notice here F minus is in fact tail to tail with the vector P, because P goes up there. So we see that was actually the right angle. But in fact, when you do that, you actually have to do the cosine as opposed to the sine, which was kind of weird. But the main thing is P cross E is supposed to be the result. If you also take work is equal to the integral of P, or excuse me, of F dl, you could also call that the integral of tau d theta. And when you do that, you end up getting basically negative P dot E. So it turns out that the potential energy U stored in a dipole being in an immersed in electric field is negative P dot E. So that's another vector form we wanted you to know and be able to use. That means you need to be able to create vectors and all that cool stuff and do that. I'm sorry this went bad. I'll just say. But you can follow the part of the book where they derive that yourself, and I think you'll see it's pretty straightforward. I don't know where I screwed up, but I was trying to, make the component of the force that's perpendicular to the lever arm, and I think that's where I screwed up in choosing the theta and whatnot. But anyways, those are the right formulas. Those will be the formulas that I put in your formula sheet for 240, 242, excuse me. And I'm slowly putting that into this practice test and that online test. So the online test will have the appropriate equations in there soon enough. They just don't have it yet. So uh, we all,
Excuse.
yeah, go ahead, Shonda.
You mean the practice test is going to have a formula sheet?
I'm trying to put them in all my practice tests so you'll know exactly what formula sheet you're going to have when you take the online or face-to-face test. So yeah, that's what I mean.
Okay, because I thought you already posted the practice test.
I
didn't
did,
see
but
a
it
formula
allows you to
sheet.
add non-point worth questions, and that's what these are. They're just formulas. So I did put them in today, and they're working
Okay.
now. You might not have seen them the first time, but they're in there now. Okay.
Okay, thanks. All right.
No problem.
Yeah.
Anybody else have any questions? All right, well, we have about 4 more minutes. I'm going to go ahead and do that circular disc. You guys are free to split right at the end of the time. The recording will continue, so you'll still have access to it. I usually post that the same night, if not first thing in the morning, so you should be able to see it. I'm going to go ahead and work that out, but like I said, go ahead and leave at 6:40 if you need to. That's not a big deal because this recording will be waiting for you. You can also find the same video where I do the same thing online on my YouTube channel as well. So you can look up those. In fact, I think I put 2 links to them in week 6 module. So let me go ahead and start. I'm going to draw my coordinate system again. And the coordinate system again is going to be a three-dimensional coordinate system. And it's going to be the x-axis coming out here, the y-axis there, and the z-axis there. And now what I'm attempting to do is I'm going to attempt to draw a circular disc in perspective. So it should be somewhat oval, which is exactly what I did, but I actually got it a little crooked. So I hate it, and now I'm going to erase it because I hate it. All right, let's try again. There you go. I just forced myself to draw on those lines. That works pretty well. So that's the actual disc, okay? And what I want is to know the electric field at this point P up here, okay? And what I'm going to do is I am going to add a little oval of charge, not unlike the ring of charge we had before. Okay, now this one is going to be dq, which I'm going to say this disk is uniformly charged over the entire surface area. That means every square inch or every square millimeter or every square centimeter will have the exact same amount of charge. So because of that, I'm going to take that amount of charge, which is sigma per unit area, that is coulombs per area is what that sigma is. And I'm going to recognize that this is sort of like a rectangle. This green hoop that I've drawn is sort of like a rectangle in that if I cut it open, it would have a length about equal to 2 pi r and a thickness equal to dr. So I'm going to call this 2 pi r dr. Notice that is the radius little r, whereas the radius of the disk is going to be big R. Okay. So that's my DQ. Now, the weird thing is there's an infinity of vectors that point to DQ. So if they're using that DQ, RP minus RDQ doesn't really work out that well. But what I do know is the electric field due to that will all be pointing upward because the X components will be canceled out like I showed you before. The Y components will be canceled out like I showed you before. So I'm going to say E is equal to the integral of dE, which is going to be equal to sigma times 2 pi r dr over 4 pi epsilon naught. And here's the most important part is how far away this dq is from z, from the point. And you can see that it's clearly a distance lowercase r squared plus z squared square root. So I'm going to say right r squared plus z squared. That's going to be to the 3/2 power. In fact, I could make that just a 2/2 power just to just since we're working with the magnitude and not thinking too much about the other stuff. Yeah, that's what I'm going to do. So when I do this one, I'm going to have the distance being r squared plus z squared like that. Now I'm going to integrate that from r equals 0 to big R, and I'm going to have to convert it by realizing that, let's say from this little spot right here, the DE points that way, but I really need the component of it along the z-axis. So I need to multiply that by a cosine of some angle theta. Well, that angle theta is always going to be r over z. So basically what we're looking at is we're going to consistently have an angle theta here, a z there, and a lowercase r there. I want the component so we can see that cosine theta is equal to adjacent over hypotenuse, which would be z over the square root of z squared plus r squared. Square root. That's what the cosine is. Okay, so we've got a z in there. That works okay, but the problem is we've got this cosine theta in there, and that is a function of r. So I'm going to put in a cosine theta there, and this is going to become sigma times 2 pi over 4 pi epsilon naught integral of r dr. And then, of course, cosine theta is supposed to be z, so I'm going to get a z on top. And then I've got a r squared plus z squared to the 1 power, but now I got to multiply it by the square root. So now I'm back to the 3/2 again. Now this isn't so bad. All I got to do is let u equal r squared plus z squared. Then du is equal to 2r dr. So we got that. I can go ahead and take this 2 and put it there, and then this would make just du. So now I'm going to have equals sigma pi z over 4 pi epsilon naught integral u to the negative 3/2 times du. You can see the pi cancels out here. That's helpful as well. And I'm going to integrate this from r equals 0 to big R. Now, the integral of u to the negative 3/2 is -2, because it's negative, what was 1 over negative 1/2. So it's -2 sigma z over 4 epsilon naught. That takes care of the multiplier. Now I just have r squared plus z squared to the negative 1/2, and that's got to be evaluated from r equals 0 to big R, and it's all going to point in the k-hat direction, of course. So now I can see the -2 and the 4 is going to cancel out, leaving a negative 1/2. So I'll say negative sigma z over 2 epsilon naught. And now when I go to evaluate this, I get 1 over the square root of r squared plus z squared minus 1 over the absolute value of z. Now, that's all, of course, in the k-hat direction, which I could have put over here 1,000 times. I'll put it in there now. Okay. So I can actually reverse this order, and then I finally say that the electric field is equal to sigma over 2 epsilon naught. There's a reason why I'm pulling the z inside. That's going to be times 1 minus z over the square root r squared plus z squared, like that. And all that's in the k-hat direction, and we're done. All right, we'll talk more about the special cases, like we could imagine when the radius is very, very small compared to when the big R is very small compared to Z, then this thing should look like a point charge. But when the radius big R is huge compared to Z, this is going to look like an infinitely large surface, and we'll get another result there. But that should do it for now. You guys are free to go. Hope you had a good time. It looks like everybody's already gone. Nope, nope. Micah's still here. Micah, did you have any questions, sir?
Oh dang, wait, it's just me.
Yep, that's okay.
Yeah, I was gonna ask you, how did you derive the dq equals sigma to r rdr thing again? You're
Okay.
talking about like the rectangle or something?
Yeah. So where I said let u equal r squared plus z squared, that's what you're talking about?
Oh no, at the top of that, it's dq is equal to sigma 2 pi r dr.
Okay, gotcha. So what we looked at there, let me show you, is if you imagine taking that thing like this and just imagine cutting it down down this line right here, what you'd really get is something that this part is 2 pi times r, and then this other part you'd actually get was a little bit longer.
Mhm.
And in fact, this part would be 2 pi r plus dr to there. And then this thickness right here is just dr.
Oh, I recognize something like that from source. Yeah.
Yeah.
Okay.
The neat thing is, and I actually cover this on my YouTube channel, but if you really wanted to figure out what that distance is, I think you can see it's pi r plus dr in parentheses squared minus pi r squared. If you work that out, what you'd find out is it differs from this formula 2 pi r dr by terms of the order of dr squared or larger. So it's completely justified in making this assumption because the Riemann sum is taken over an infinitesimal dr.
Yeah, that's right. Okay,
Okay.
that's cool. Thanks. I'll see you tomorrow morning in lab.
All right, sounds
Thanks.
good. See you, Michael.
Yep.
And that's it. Bye bye, everybody.